All right, so in this video lesson here we are at we're looking at the partial derivatives here. Okay, so as a requirement in order to move on in this lesson here, in this particular lecture, then it is required that anyone viewing this lesson here must be already fluent with what a multivariable function is. So you must watch my other video lecture where I deliver the understanding about a multivariable function, and then here we are ready for the partial derivatives. Okay, and so needless to say, this lesson here is only intended for the students who have already passed the level of the single variable calculus and particularly the integral calculus. Okay, so here we arrive at the multivariable calculus and specifically looking at partial derivatives. All right, and so now to maximize the amount of board space, right here I am going to erase the discussion title, and I won't get directly into the pointing out what it is yet. Okay, and we will start exploring the ideas through a few problems that demos the ideas, and then we're gonna start getting formally into what a partial derivative is. Okay. All right. So in order to have a clear, solid understanding of what a partial derivative is, now let's just even though I said earlier that it is required that anyone learning in this lesson must have already learned about what a multivariable function is, but how about at this point right now, let's put all of that away. Let's put all of that aside from away from our mind right there. Let's just roll back in our learning. Let's roll back in our learning to the point where we first learn about the derivative. Okay, when we first learn about the derivative. And so we picked up a few power rules and product rule and chain rule for taking derivative. Like I said, take yourself or pretending that you're taking yourself back to that time point where you already just learned some basics of finding derivatives on a single variable function. Okay, then let me put in the following problem right here, and believe me, as you go through with me, you will have a clear understanding what I'm trying to do. Okay. So now how about, at start, allow me to demonstrate with the following function. Let's say we have y equals ax squared. Simply just that, y equals ax squared. So now, when you're looking at this function here, the way how we have been understanding so far, and again, as I said, let's for now put away the understanding about multivariable function or anything like that. Let's just simply put away all of that understanding about multivariable function, even though it is already required that you should have learned that prior to getting into this lesson. But now, in seeing this function here entirely as some function in terms of one variable, then of course our mind is more comfortable, our mind will work more comfortably to see x here as the variable, and so the a here is some coefficient. Okay? And so now, here it just describes some general case that this function is a quadratic with some coefficient a. A quadratic coefficient, a quadratic function in a sense that the variable here is being square, okay, and then it has a coefficient a multiplied in front. And so from that understanding, the professor in just an ordinary calculus course, a differential calculus course, would ask the student to do the following. So think about if we have a function y equals ax squared. Okay, then let's find dy dx. So at this point in your learning, and especially as I have mentioned, anyone viewing this lesson should have learned and become fluent with the finding the derivative. Should have learned and become fluent with the differential calculus. Then looking at this notation is simply, is something quite easy for anyone. Okay, it's simply a very, easy work right here. This notation is telling anyone reading the problem some instruction that, hey, in this relationship right here, in this equation written right here, we want y to be in the role of the function. So So here again, I'm making that notation. We want to emphasize that this notation emphasizes that y is being regarded as the function. Okay, and so now the dx in the denominator is indicating that the x variable, the x letter in the expression on the right hand side here is regarded as the independent. Okay, that's the independent variable. All right, so y, the value for y, the output for y is dependent on the value we chose for x. And so in this case, if we're reading this notation, then we primarily only concerned about the y variable as a function and the x variable as the independent variable of the function. Even though a is still not given, a is just another letter out there, but our mind, think about again, if you roll yourself back to that time point where you learned, where you were in your process of learning about taking the derivative, then so at that point, at that time point, we only saw that a as a coefficient. Okay, and so if we take a simply as a coefficient, and your instructor, or I am being the instructor here, asking you to find dy dx here, and we already understand clearly, we have already understood clearly the meaning here. So in this symbol, y here is indicated as a function, is understood as a function, and x is understood as the independent variable. Then now we can proceed easily. We can proceed easily with our understanding on how to find a simple derivative. So the derivative like this is quite simple. So now dy dx equals, so the power rule says we multiply the power down and together with the other coefficient that has already been there, So we're looking at 2a times x. Okay? End of story. End of story. That's it. That's it for dy dx. So we got the dy dx came out being 2 times a times x. And so we follow strictly just the rule to take the derivative. Nothing should be surprising to us. All right. And then so what about that a right here? Just think about if the a was previously given like a 5, then here it would be a 2 times 5, meaning it's going to give us a 10 times x right here. That's our final derivative. But here a just simply given as a representative, as a general coefficient. So any particular value for a is not given. And so in that way, the derivative is also involving a right here, because we still did not have a value given for a. So we leave a there, but we treat a as a coefficient. All right. And so that's the end of the story at the level when we were doing the single variable calculus, or particularly we were doing just when we were beginning to learn about differential calculus, taking the derivative. All right. And so now, same function. And then we're not done with this little simple problem yet. Same function. So now let's ignore all of the work we have done here. And in the meanwhile, I am going to move on to the other board. So on this side of my board, allow me to write down the same function again. If y equals a times x squared. A times x squared. But now at this point, I want anyone learning in this lesson to look a little further, to look a little deeper into the situation here. So we got earlier in the work we primarily treated x as the variable, and we treated our function as one single variable. And then of course y is the dependent variable, that's why it was a function and it is still a function. But now if we're looking a little deeper into this, in the end, the a here, the a that I'm leaving here, it's a letter, and that letter represents any possible coefficient. It could be a 5, it could be a 2.5, it could be a negative 10, it could also be a 0. So what I'm trying to point out now in front of everyone is that can this a, because it's a letter, just like the x, just like the y. So how come in the earlier problem, my concern now is that how come in the earlier problem we only treat x as the variable and completely ignore about the y? I mean completely ignore about the a. And so now as we start thinking a little further, in a general situation like this, then why not also considering a as a variable as well? So the concern being raised here is, can a be a variable? Can a be a variable? Sure, why not? It's just a variable. If we can target a, so now I'm going to say the answer, yes, sure. A can be a variable because clearly just earlier I was pointing out we can assign a to be a coefficient 5. We can assign a to be a coefficient -10. We can assign a to be a pi here. We can just give any value to a. So in the end, a can be another variable. Sure, why not? Okay, and so upon clearing that understanding, upon breaking away from that habit that seeing a only as a coefficient, yes, if we are treating x as a variable, then a can be a coefficient. But in the end, if we're just simply looking at the whole thing through, then x is a variable, and now also a is another variable. So in that way, now allow me to lead anyone's attention into this new direction right here. So we were able to find dy dx. I still recall that correctly. And that work is still on the board here. We want to treat y as the function. We want to treat y here as a function. But we want to treat x here according to that notation. We want to treat x as the independent variable. And then in that derivative, then we treat a, we saw a, we regarded it to a completely as a coefficient. Okay, so now back on this side of my board right here. Since we all agree between I'm teaching in front of the camera here and with anyone viewing the lesson, since we all agree that a can surely be a variable, then can we find dy dA? It's a variable. Changing the value for a will also change the value for y. Just have some thinking of that. It's a variable as well because we said yes, it's a variable, and now I can still defend my reasoning right here. Changing the value for a will change the value for y as well. So think about our function here, y right here equals ax squared. If we give a equals 5 and x equals 2 right here, then our y value is 5 for the coefficient times 2 squared. That gives me a 20. Okay, same general setup right here, same general formula right here. I can provide, I can let a given to be a -2 and x equals 5. Okay, then y value is -2 substituted for a, okay, times 5 all squared to be 25, and 25 times -2, that gives me a -50. So having a value given for a also together with a value for x changes the value for y. And this is now where you can start putting in some of your experience with multivariable function involved in here. Okay, but that's still a long journey from now. At this point, I'm not expecting much about this. I'm not expecting much about you are bringing in your experience with multivariable function. But just right now, focus right on this notation. So in this symbol right here, I'm saying dy, let's find dy dA. So in that same understanding I've been giving, in that same explanation I've been giving throughout all my time teaching about the differential calculus, then seeing this notation that was derived from Leibniz right here, then dy is indicating that y is regarded as the function. Y is being regarded as a function. But a, it's a variable, it's a letter, it's a variable, and a being regarded as the, okay, I have to double quote this. So a is being regarded as the independent allow me to just write it short, independent variable. All right, And so in the way now, once we're clear with this understanding, so in the way how it is being addressed right here, how this notation is addressing for us, we want to find the rate of change. Well, derivative at this point, this is clearly a symbol for derivative. Okay, needless to mention about that. So this is the derivative, but treating y as a function and a as a variable. So in that case right here, what about the x squared? What about the x squared? All right. What about the x squared? Okay, what about the x squared? So now let me take you back to the other board and put in some more detailed explanation right here. So earlier, when I was asking any one of us or any one of my students to find the y dx for me, things happen fluently. I mean, I could have also raised that question earlier when we were looking at this and focusing on x as the independent variable. Then I could have also asked, what about the a variable? At that point, if I raised that question, anyone would easily tell me that a is being regarded as a constant coefficient, and that's why we consequently ended up with this. All right, and so now just simply think about in this new situation, everything switch role. Everything just simply switch roles. So now it's pretty much exactly the same problem. I want to find dy, but now dy dA, the derivative in respect to a. So I want to target a as the independent variable. So now I officially raised that question, that concern. So what about the x squared? And so now the x squared, just think of this. Yes, mentally, psychologically, any one of us is more comfortable with understanding a coefficient being in front. And what got a lot of my students hung up in my experience, in my teaching experience, what got my students hung up in a sense that it's hard for them to take this truth is that the x squared stands behind the a right here. Okay? But in the end, let me now remind anyone learning in this lesson, it's a product here. So a times x squared, a stands in front of x squared, is also the same as the product of x squared standing in front of a. I'm doing this for a purpose. Now x squared in front of a, and I further see a as a power 1. How's that? Okay, and now we want ultimately as a goal in this problem, when I want to do a dy dA, treating a as the independent variable. And so now back to that concern that was raised just earlier. So what about the x squared? If we now treat a as the main variable, as the main independent variable of this function, then what about the x squared? So now we're going to treat the x squared, right, is as a coefficient. X squared could be some whatever value that is, so that x squared can be a 5, x squared can be a 10, x squared can be a whatever. It's a coefficient. Okay, as a coefficient. All right, regarding to x squared, that's the answer to this concern right here. X squared can be regarded as a coefficient. Just exactly like that situation when we were still doing y equals ax squared and we were finding dy dx, and we treated y as a coefficient. And just now, if we switch role of these two variables, then we can just simply target at a being the variable, but we're going to the idea now more generally, to extend the idea now a little more generally, is that anytime we already have a variable of main focus once, so this symbol is so powerful, it routes our attention, it grabs all of our attention to focus primarily on that variable. And once we narrow all of our focus into that variable, everything else in the same product, everything else in that product is considered as, see here, it's not just one variable, it's like an expression of the variable. But see, this is everything else but a. Everything else aside from a. That we regard as a coefficient. All right, and so now in that way, now once we have it clear with these, once we have cleared among instructor and students, okay, then now allow me to erase this work, or maybe I can just now put this away and leave this part right here because I feel it's important. Okay, So this dy dx, now we can have the following answer. All right, this dy dA right here, this dy dA, now we can have an answer. If we now agree between each other, that between instructor and students, that this is a coefficient, then I'm going to leave the coefficient the same, x squared, and I'm going to multiply the power down in front, so 1 times x squared times a to the 0. The power rule simply applies here. The power rule simply applies here. So consequently, my derivative dy dA now turns out to be just simply x squared. All right, so ladies and gentlemen, dy dA, so how about let me write it a little closer, and then I'm going to have some space. So conclude as a conclusion right here, dy dA we have found to be x squared. All right, dy dA we have found to be an x squared. Okay, because we just simply applied the power rule, but when we were taking this derivative, we particularly focus on a as the variable and everything else. So the point now is that, see, I raised that concern here. What about the x squared? But more generally, I want to emphasize that x squared here represents, in this product, everything else aside from the main variable expression. Everything else is considered as a coefficient. That's the key idea right there. Okay, and so now, ladies and gentlemen, let me clear out the board, and then I'm going to kind of generalize the whole idea here. All right, with this function y, and now I ask anyone viewing the lesson here to bring in your understanding with multivariable function, because I have spent time just earlier to argue that if we can traditionally see x as the variable, why can't we see a here as a variable as well? And now once you realize that, hey, we have no reason to disregard a as another variable, then all of a sudden we realize that y is a multivariable. And precisely speaking, this is a function of two variables. Y is a multivariable function. Okay, and we can, so y equals ax squared, we can define a function f of x comma a, for example. F of x comma a, and then that equals a times x squared. Yes? Now, or certain something that we work so fluently in any math courses up to the differential calculus and some integral calculus prior to this point. And then all of a sudden now we realize we can also regard to this function as a multivariable function. Two variable. In this case, we have a function of two variables. The a as a variable, which is in some cases it can be acting as a coefficient. And then the x squared here is another variable. The x here is another variable. All right, so now in that case right here, ladies and gentlemen, this dy dx, because in the end we call this here is a y. Okay, so the dy dx, but I don't want you to tie your mind down to this symbol yet, because I'm using a friendly symbol. But then eventually I will have to lead your understanding into the correct and the proper symbol, the proper notation where the rest of the world outside of our lesson is also using. So this is not the correct symbol yet. But now as far as if this is the function a times x squared right here, then the dy dx in our limited understanding, we are understanding that we're treating y as a function. Yes, clearly it's a function. And we're taking that derivative of y in terms of x. Okay? And then so that means we're treating a here. We're treating this a here as the coefficient. Just anything else, any other expressions that not involving that's aside from the x variable, because we turn our main focus to target on the x as the variable. So if that's the case, we're treating a or anything else as the coefficient. So in that case right here, we found the dy dx here being 2ax. But then on the other hand, we also found same function. We want to treat y as a function. But now the y here, we realize just further, y has two variables involved. And we are at that mixing point, that point where we bring some mixed understanding between just function of one variable, and now with our new experience about function, multi-variable function of multiple variables like that. Okay, here I'm working with two variables in this case, but so in the end, if we're seeing y as a function, and now but here we previously did dy dA, that means we target at the a variable to be the main variable, the main independent variable that drives the value of our function. Then in that case, aside from the variable a here, everything else, even though being an expression, is regarded as a coefficient. Okay, so in that case, and that was the reason why I came to earlier from the other board, I came to the dy dA here as being just x squared. So that's just a result. If you need to, feel free to roll back on the video to see how I explain about that. All right, but see, so now with a function of two variables, we ended up with two different kinds of derivatives right here. Two different kinds of derivative. One derivative is in terms of the variable x. This is the one. So if that was the case, if that was the derivative particularly or intended to be in terms of x, then we're treating all of the expression aside from the x variable as coefficient. That's the case. Okay? And then on the other case, if we were finding a derivative, formally speaking, in respect to a, meaning treating a or targeting at a to be the main variable, then aside from the a main variable, then any other expression involved in the same products here, any other expression aside from the a variable that does not involve a, we can regard to that as coefficient. And that was the reason why earlier on when I was on the other board, I was treating a here as a power 1, and then power rule came down, so we consequently end up with an x squared. So the situation may be a little bit hard to see at first, but just think about, think about we have a function y equals some a times 2 squared. Or maybe 2 squared, the number 2 is a little too special, so how about 3 squared, okay? See, this can be some x squared right there. But now dy dA, if we focus on a here as the variable, then if that's x squared or 5 squared or 3 squared whatsoever, we treat that as a coefficient. And we may also write that in the back. When I was on the other board, I was showing that we have our right to turn the product around using commutative property of multiplication. And so in the end, see, dy dA equals just simply 3 squared, because this is power 1 for a, and we apply the power rule only on the main variable. We don't apply the power rule to the coefficient. That's the idea right there. All right, so now once again at the bottom line, I now tell you, ladies and gentlemen, whoever learning in this lesson with me right here, this function with two variables, we ended up with two kinds of derivatives. One of them is and each one of them, how about that? Each one of them is in respect to one corresponding variable right there. So here I got dy dx to produce this, and here I have a dy dA right here to be corresponding to that a as the variable. All right, and so now I started to say it. This function here, we got two different kinds, and because we got two variables, we got two different kinds of derivatives right here. So now precisely speaking, this one right here, this one right there, allow me to now use a red ink right here. You can notice I use the brackets just to include the derivative part, but I'm kind of excluding out the dy dx symbol, because I will erase this out and write down the correct notation, because as I said earlier, this is not the correct notation yet. But anyway, the result we have found here, it was a derivative. And I explained earlier, it was the derivative in respect to x, because we turn our focus, we target on the x as the main variable. So now this is, but then in the whole function, we regarded the function here as a function with two separate variables, and this derivative was only targeting at the x as the variable. and ignoring the other guys, ignoring everything else aside from x, and leaving those as coefficient. That's why for this kind of derivative, we regard to that. For this kind of derivative, we call that, this is the partial, all right, the partial derivative. All right. Partial derivative of the function y, okay, in respect to the x variable. This symbol right here, it's called the partial derivative. All right, underline that. I wrote it in red ink, and I also want you to underline that. Whoever learning in this lesson right here, underline that term. It's called a partial derivative. See, it's a derivative, just like any other derivative you have learned. But why do we call it partial? Because it's relative to the whole function, which has more than one variable. Then this derivative only focuses on one. That's why it's a part. And so altogether here, the precise name, partial derivative. All right, so it's a partial derivative treating y as a function. That's why the way how it says is pretty standard wording right here. The partial derivative of y, meaning y is a function, just like how I have been explaining. Okay, in respect to x, that means we want to treat this as the derivative, but treating x in our function here as the main variable in respect to x. That's what a partial derivative is. So when it comes to this, in my style of teaching this material for years right here, I tend to give up on formal worded definition of a partial derivative is defined to be such and such and such. I'll just show a problem, and then once you understand the idea, that's what it is. So this product we found right here, this work we have found, this result we have found is now called the partial derivative of this function. Okay, defined as a times x squared right there in respect to the x variable. All right, and so that's what it is. And now I'm running a little narrow in space, and I do not want to erase this because I wrote it down not too long ago. So I'm going to spend some time writing down a lot of this structure again on the other board so that I can explain about the other one, how we call that one. Okay, and in the end I still have not shown. So right now, again, even though you might have taken some notes, but leave me a room to come back and fix this and change this to the most correct form of using notation. Right now it's just the notation that I purposely use so that it's friendly to anyone learning. This is a notation that anyone learning right now is very friendly with that notation, meaning so familiar already. But then honestly speaking, this is not the correct and not the proper notation yet. It's not the proper notation that math people worldwide are using out there. Okay? All right, so now on this board, again, just that. I'm leaving that line y equals x squared, ax squared. And yes, we have already agreed that this is a multivariable function, a function of two variables. Okay? So y is a function of two variables. A little bit unlike how I wrote it in the other side of the board right there. But now, so we found that dy, dA, we found that to be x squared. We found dy, dA to be x squared. And so now this final result that we have found, and there were so much explanations earlier already, so I hesitate to go back and restart all of that explanation again and repeat all of those explanations. But now this final result right here, it's one of the derivatives among the two derivatives we found. All right, we got two variables, and we ended up with two different styles, two different derivatives. One of them was in respect to x that I showed on the other board, and one of them is in respect to a that I have it here right now, and we got a lot of explanation that I already erased. Okay, but now formally as a name, I call this part that I underlined right here with red ink, this is called the partial derivative Okay, the partial derivative of the function y. Okay, but now this time, see, the main variable that we target is here, the a variable, not the x. So now I'm going to say in respect to a. In respect to a. So this is the partial derivative of the function. This is our objective function right here. We want to target on a. See, a was one of the two variables right there. All right, so we have this is partial derivative in respect to a. So our function here at start, is having two variables involved, and so in that way we found one partial derivative in terms of x, and then we found a different partial derivative in terms of a right here, because our function only involves a and x being the two main variables, being the two variables. That's the idea. So that's what partial derivative is. All right. So now it's time to reveal that truth. It's time to tell anyone viewing the lesson here that truth about the symbol. So I've been writing it down, but surprisingly or shockingly to anyone that I keep telling you that I'm not using the correct symbol yet. Okay, so I apologize to anyone who has been taking note that you may have to erase some of your notes here, but again, my purpose so far is to bring back something that you have been familiar with, okay, and for you to understand and hopefully make the transition into partial derivative smooth. But now, when it comes to partial derivative, we don't use the straight d like this anymore, okay? When it comes to partial derivative, even though the meaning now, hopefully anyone viewing the lesson up to this point is so clear about the meaning of what a partial derivative is and what it does for your function, okay? But now we don't use the regular d right here. It's still the dy dx or the dy dA here in this demonstration, but instead of the straight regular d like this, allow me to write the proper symbol. All right, and once I finish writing it down on the board, if you cannot recognize my writing, I don't blame you. Hop onto Google and ask Dr. Google to show you how to draw a partial derivative symbol. It will show you, okay? But basically, so y is your function, and you want to draw a dy dA, but it's just some kind of fancy d that indicates it's a partial derivative, not just any ordinary derivative like we've learned in single variable calculus any longer. So instead of writing instead of the regular d version like this, nope, we write the d as following, kind of like a sideways 6 right here. All right, so it's a d, see, a curly d like that. So that means, so now my dy dA is looking as following, dy dA. Now welcome to the world of partial derivatives. That is the partial derivative dy dA. You can just still say straight dy dA, but the way we're writing it, it's a little bit different, or maybe quite different with the ordinary dy, d whatever symbol. So this is old days for single calculus. This is partial derivative. All right, this is old days, and this is for single variable calculus for single variable function. But this is derivative, so d or dx, but now d or whatever dx. Okay, this is partial derivative. All right, so just like that, now I can switch back to my other board. So on this board, again, this symbol was not correct yet. That symbol I used, I just want to enforce the main idea here. But now as far as once you're fluent with the idea, hopefully, then we're still going to say dy dx. But sadly, we don't write the symbol like the old days anymore. We write the symbol as following. It's a d, but a fancy d. All right, dy, and now dx. Okay, and so yes, what is this? Or what, as far as what this is, it's the partial derivative. That's result right here. That's the result. This is just a symbol. This is just a notation indicating what we want. Okay, so we want to find the partial derivative of y in terms of x, in respect to x, targeting at x in our beginning function here as the main variable. And so now in that case, we treat the bottom line is the important key is we treat anything else aside any other expression in the same product here aside from the x here as the coefficient. So that's the coefficient. So now partial derivative of y in respect to x, see, I target on x as the variable. Everything else, coefficient. And this is the symbol now. All right, and then on the other board, this is my partial derivative, but in respect to a, because in that function, now tentatively a two-variable function, intended to be a two-variable function, then I treat a as the variable, because that symbol, once we're reading it, dy dA, yes, we call it by name. It's a partial derivative of y in respect to x. So much wording, but in the end, it tells me that we want y as a function, as a function, and then a here is as the variable, mainly as the variable. And then, so that's why, so what about, like I raised that concern earlier, what about the x squared? It's just simply an expression that no longer involves x. The expression of everything else but a. Okay, I might have accidentally say x, but here I'm talking about it's the expression that's aside from a, because a is our main variable at this point. So the entire expression that's aside from a, we call that a coefficient. And that's why, so now if you see the whole x squared here as a coefficient, then a here is simply just power 1. 1 multiplied down, multiply with a coefficient, and then subtract the power by 1 here. Okay, so that's why we have times a to the 0. So the entire partial derivative here is only an x squared. That's how it is. All right, and so now after this demonstration right here, this demonstration, and now surprisingly a function, a y equals ax squared is now shockingly seen as a function of two variables. Okay, and so now I can show another demonstration problem right there. But now, maybe before I'm heading out to another demonstration, before we are ready to do some examples, then let's introduce another convention right here. So yes, as far as the naming, we know it. Allow me to erase how we call these things. That's just how we say their name. So now let's look a little more about the symbol. All right, so I wrote earlier on the other board that this function, you can also see this as, I need some space here, so this function on the other board, I also wrote that as y equal to a function of two variable a comma x, and I mean x comma a, okay, and equals a times x squared. So just like that, and everything you've learned in math up to this point, let's bring it in. But this is one way of writing a function. And now, even though we're working with multivariable functions, okay, anything we have learned in the past, we can still bring it back right here. One way we can write a function expression is that just simply y, one variable, equals the expressions on the other of the main variables or main variables on the opposite side. That's one way. But we can also write our function notation in this way right here, where we name our function and then indicate the pair or the triplets or the n tuples of the variables. So this is in functional notation. So anyone viewing this lesson should be familiar with this. So when your function is written in functional notation, then so if it was written y equals or z equals, just one variable equals your function expression immediately, then we use the partial derivative symbols here. That this idea here came out from the Leibniz symbols again. I don't think this was the Leibniz original idea anymore. Now the dy dx symbol originally was from Leibniz, but partial derivative comes a lot later. Okay, and so but it adopts that convention from Leibniz right there. Okay, but that was we use this symbol corresponding to the case where our function is written in an equation form like this. But now if our function is written as, okay, so I'm going to create a separate space right here, kind of like a separate world. If our function was written f of x comma a to equals ax squared, then an alternative notation is the following: f with a subscript x. Well, yes, having the input indication or without having the input indication is not too important. But when you see f with a subscript x, That's another notation and quite commonly used as well. So I cannot really say, which one among the two here is more commonly used than the other one. They're both they're both commonly used. So be ready to use and understand these two symbols interchangeably like that. Okay, so F prime, we just don't use the F prime symbol anymore. So at some point when you hear me accidentally say F prime, that means my mind at that instant is still stuck with the past understanding. All right, but now we don't use F prime. That's the one thing. It's good that I accidentally had that thought saying F prime so that I can also remember to tell anyone. We don't have F prime idea anymore, but instead, see, this is equivalent to F prime right here. But this is an F prime in respect to x because it's a partial derivative. If you just simply say F prime, then hey, back in the world of one variable in our function, then yes, F prime just means by default, whatever variable mainly there, that's your F prime. But now because we have so many variables involved, and any one of the variable can be equally, as a chance, any one of them can be equally likely to become, the variable in the derivative. That's why we have to now clearly specify partial derivative in respect to x, partial derivative of f in respect to x. All right, we don't really say f prime anymore, okay, when we're getting into working with partial derivatives. All right, and so similarly, we can have the dy dA that's written on the board here. We can call that f with the subscript a. This is the partial derivative of this function f, taking a in respect to a right here. And yes, writing down the input indication or without writing down the input indication, that's not important. Having the x comma a here is not important. But these two are the other style of writing the symbols right there. All right, so that's what we've seen about, and that's introducing anyone viewing the lesson to what partial derivative is, what a partial derivative is of a function. All right. And so now I still want to give one more demonstration problem for you to get a really good hang of that, so that you can hear some more explanations before we head into some actual examples where we get an opportunity to do some practice problems between instructor and students. Yeah. Okay, so what about some function as following? We can come up with a function. How about f equals some p times e to the kt. All right, I purposely brought the function. Made the function a little more complicated, or indeed, how about let's forget about f. I'll go with z. Z equals p to the kt, and p times e to the kt, and p is capital letter or lowercase letter, your choice on that. But be consistent. If you chose to work with lowercase letter instead of capital letter, then later on, anywhere we get to the p, then you go with your convention. I stuck with the capital P, then later on, anywhere I refer back to p, I'll use the capital letter P. Okay, so, but now this is a function of three variables. So this here, upon defining it, all right, this is or how about, let me write it down here, is a function. So z is a function of three variables. All right, and so at this point right here, needless to say, and I mentioned that anyway, see, it is strictly required that you have to now have some experience, or at least have learned something, okay, about multivariable function right here. All right, so now it's a function of three variables. We have learned in our specific discussion about multivariable function. Once we can take that idea about a function can involve two variables, then why not three? And why not even more? So here, let's, in this demonstration, let's get some experience with the function of three variables and how we can find the partial derivatives. And so now, a good amount of explanations was given already in the earlier demonstration. So here I can start speeding up the pace a little bit. So realizing that this z here is a function of three variables, okay? And so in that way, and you can also see this as z equals some f of, see, I see three variables in here. There's a p, there's a k, and there's a t in there. E here cannot be a variable because it's a letter, but in this case, in math, we have already decided long ago to reserve the special letter E for the constant 2.718 and a lot longer. So E is by default. So anyone worldwide seeing E as a constant. Nobody sees E as a variable. All right, so we only have 3 variables here, but see, the idea now is that switching to a different triplets of these 3 values right here will cause a different output for Z. And that's why Z here is clearly a function of 3 variables. F is the name of the function, P, K, and T. All right, and the rule for the function here, is P times exponential of K times T. It's a K times T here. And so now right here in this problem, let's look at let's find how about so let's stick with this form earlier, so we can call this dz. So now you understand that I'm about to ask for finding the partial derivative. So find dz, how about see, so out of all 3 letters, really at this point no x present. I purposely brought it in like that, so no one's mind is going to be tied down to x is the variable, x is the variable. We got all of these guys right here. So any one of this can be a variable, and any one of these is a variable. So I can just make my choice right here, dz, dp. It's a partial derivative of z as a function in terms of the p variable. All right, so if that's so, now then let's repeat what we have learned from the earlier demonstration right there. So now in this function that we're looking at, either you can look at that version or this version right here. Let's turn our focus to this p right there. And then it's a product, everything is product and power, right? Simple enough function. And so now with that being the main variable, and it's multiplied, it's in product, this variable here is in product with some other expression. But the good thing in that other expression here, no more p letter involved right there. All right, so now we know that the entire expression here can be regarded as see, that one here is now that's as a coefficient, one big huge coefficient. That's the idea right there. All right, so if we're taking that as a coefficient, then really the p here is only raised to power 1. And so now taking the derivative in terms of p, or more precisely the partial derivative in terms of p, and I'm looking at e to the kt, because the power multiplies down. So how about one more step that I can fit in to really clarify the idea. Okay, the power 1 multiplies down, so I'm looking at really 1 multiplied with p to the 0. How's that? Times e to the kt. E to the kt stays just the same because it's a coefficient. Okay, and now 1, the power previously multiplied down, and then the power now is reduced by 1. The standard the standard power rule that you've been using throughout your whole time learning about taking derivative. And so that's why I end up with e to the kt. This is now legally, I call it, it's the partial derivative of z in terms of p. All right. And so now, let's find another one. So the next one. So here I'm looking at, how about let me use my other board. All right, so the function we have here, yes, it's z equals p times e to the kt. 3 variables, right? And so now let's find, how about this time we want to find dz, dk. That's my letter k, dz, dk. All right, so k is a variable in this function right here. Okay, k is a function, a variable in this function. Z is the function, and k is the variable. And this notation is making it clear. Z is a function, k is a variable. And so if we now turn our focus to k being the variable, then everything else is coefficient. So this is a coefficient, and this is the coefficient. The t is the coefficient together with k. So you can think of this as, you can think of that as p as a coefficient in front of the exponential term multiplied with, how about, tk. I'm doing this for a reason, because if anyone's mind is tied down to the fact that coefficient has to stand in front of the main variable, then there you go. Kt, you can rewrite it as e to the tk. Okay, so now clearly t is your coefficient. So now, and p is a coefficient even in front of the exponential term. Okay, so now dz dk is going to be, we keep the coefficient the same, just like that, and now we're going to mainly handle the derivative of e to the t times k. It's an exponential function here in terms of k, treating t as a coefficient. So I'm moving on step by step right here. And now, so in my next step, I'm still keeping that p right here as a coefficient. But the rule for taking derivative of an exponential function, anyone learning up to this point has known clearly enough. It's going to be e to the t times k. Okay, we're repeating that. And, but wait a minute, the chain rule, because there's the outside function is e to the something, and then inside of that is some expression t times k. So this is a function inside right here. So now the chain rule says we have to multiply with the derivative of the inside. So the derivative of this, okay, so the derivative of this is going to be the partial derivative of that t times k right there. But treating k as the coefficient, treating k as the variable, and then t as a coefficient. And that's why now finally in my next step, okay, p times e to the kt, okay, but times t right here. So making it shorter, p times t, all coefficient stands in front, to kt. That's our partial derivative. Okay, that's how we're doing it. And I'm really trying to break it down the steps right here, but just see that as the point is bring all of your understanding of finding derivatives from the past learning right there, from your past understanding into this. Okay, you don't have to really tear it down to all of the detail, apply the partial derivative in each little step like that. This is just for my instruction, the purpose only. Okay, but when you're doing it, you just know, hey, we keep the coefficient, and then we take the derivative on the main function here. And then as we're doing that, there's the outer functions, the derivative of the outer function, which gives me this. And then there's now the derivative of the inside function, because of there's a chain rule applied here. All right, so now I'm going to erase this work right here and write down the final conclusion. All right, so that's because I need more space in this board for another partial derivative. So now just now we found dz dk, so that was p times t times e to the kt. So there's our partial derivative in respect to k right there of the function z. All right. So on the other board earlier, I was finding dz dp. That's one partial derivative. Just now I have found dz dk. All right. So, and be aware again that our function has three variables. Okay, a function of three variables. So that means we can expect one more partial derivative. So how about dz dt. All right, dz dt. So just like that. Now it's right there. T is the variable inside of the e to the something function right there. So p in front here is clearly a coefficient. The k in this expression, k is also regarded as a coefficient. Why is that? Because this indication told us, instructed us to focus our attention to the t, treating that as a variable. Everything else, either a whole expression or just one single value, everything else is a coefficient. Okay, and so in that way, so now let me speed up the process here. It's going to be p, because it's coefficient, times the derivative of this, which is e to the kt. But then there's an inside right here, so I'm going to multiply. But remind yourself, we're taking the derivative of that kt right here in respect to t. So k is the coefficient. So that means now multiply with k. So that gives me p times k times e to the kt. That's our partial derivative in respect to t. Partial derivative of the function z in respect to t. That's how it happens. That's how it happens. All right. And so now at this point, you have seen enough demonstrations there, okay, and as far as symbols. And so now, so rolling back a little bit to clarify about the symbol used here. So I use that notation, but at some other point, I can use the other symbols. So I emphasized here this function can also be regarded as a function f of three variables p, k, and t. And so this dz dp notation, some other time I could have also written that as f with a subscript p. All right, that's a symbol for partial derivative of the function f in respect to p here. And that is that is of the variable p, k, and t. Okay, and that equals e to the kt. That's one way of writing that. Okay, that was our result. All right, and then on the other board, what we have just found earlier, I can also see this as see, our function here is f, but then taking k as the main variable, and we here find the derivative, the partial derivative. So now it's going to be f with a subscript k here, okay, of the variables p, k, and t. All right, and then this bottom one right here is understood as f with a subscript t right here of the variable p, k, and t. That's how it happens. That's how we're doing it. All right. All right, so at this point, let's head ourselves into example 1 right here. So the whole idea of doing examples now is it's a place, it's an opportunity for anyone watching the video here to work side by side with me as I'm going through these problems, and it's also a chance to formalize the steps like that. Okay, so example 1. All right, so in example 1, let's say we want to find. So how about f of x, okay, or dz dx, okay, and we also want to find f sub y, partial derivative of x, partial derivative in terms of y, okay, or dz dy, okay. So we want to find those derivatives. So there are two partial derivatives here asked to be found like that. So that means do expect that the function will be just mainly two variables throughout the entire example 1 right here. All right. So now allow me to bring in part A of the example. All right. So now our function is f of x, y. How about I'll say if right here. So we want to find that, the partial derivative and that partial derivative, these are the equivalent symbols right here. If the function is defined as, how about minus x squared, okay, minus 3x y to the 6 minus 3y squared, and I mean 5 y cubed actually. Okay, so I had that on my lecture notes but then I had a little bit of hard time seeing it. So minus x squared minus 3x y to the 6 minus 5y cubed. Okay. So it's a function, clearly it's a multi-variable function which has two variables involved in the problem like that. Okay, so now in that way, all rules of taking derivatives apply here. So here we got 1 term, 2 term, 3 terms. Okay. So just something for you to be aware. So now when we proceed into finding any particular partial derivative, okay, then we're gonna just take the derivative term by term. So let's start out with finding the partial derivative in respect to x first. Okay, so now here's how I'm doing it. And allow me to assume that you are already fluent with taking the usual derivative. Okay, so that indication is telling me that I want to focus in this entire function right here. Even though two variables involved, I only want to focus on x in each term here. Well, mathematically speaking, sorry that I'm leaving the main topic a little bit, but see now a term will always involve either just multiplication, division, or power. So adding and subtracting is to separate the different terms, in case you forgot about that. Okay, And so now, on each term here, first term, now I only want to focus on the x as the variable, and I see nothing else. So that means it's just as usual. This term right here is a terms of x. So taking the derivative on that in terms of x, taking the derivative in terms of x, it gives me minus 2x, as we used to know. So there's no need to go into detailed steps right there. Just like, as I keep asking, take whatever you have already known about doing your derivative into this. Okay? All right, and so now minus, and then the negative sign is because we had a negative sign in the first term. That's why it's all there. Okay, and now I'm going to subtract. The next term here now, the next term, that's why I was kind of, took an off track earlier and explained what a term is. So in this term we have 3 times x times y to the 6. But our mind right now at this moment, our mind only needs to focus on x as the variable. On x as the variable. And so aside from x, meaning in this whole product, aside from x, we have a 3 and then times a y to the 6. All of that is a coefficient. So it would maybe be beneficial that we write 3y to the 6 times x. That would make it evidently clear that the whole 3y to the 6 here is one package of coefficient. All right, so now in that way, now I'm ready. So now seeing that and agreeing that to be just a coefficient, then this is power 1. We multiply the power down, so my derivative becomes just simply 3y to the 6. Because now once we see all of that as a coefficient, like that, like a 2, then 2 times x, when we take the derivative, we have 2 remains. 3y to the 6 times x, when we take the derivative, treating that as a coefficient, that 3y to the 6 remains the same. Just the x is changed. All right, and now we're heading out to the next term. The next term is one term, and there's no x. And so if there's no x, that means what do we do with a case like that? We are seeing this as a constant, like, plus 5 and take the derivative of a constant, 0. Plus 10, take the derivative of a constant, 0. So minus 5y cubed, but now we saw that our mind now focus only on x as the variable. But since there's no x involved here, that means this term here is a constant. So what do we do with the derivative of constants? It goes to 0. So yes, ladies and gentlemen, the final derivative here, f, the partial derivative of f in respect to x is simply just 2 terms, minus 2x minus 3y to the 6. That's how we're done with the first one, right there. All right, and so this is one word in the problem right there. And then you see back in the instruction, the worded instruction of this problem, see the whole point of coming up with examples so that we can formalize our understanding and really put everything in place. Okay, because explanations were given, but then if it feels scattered for anybody, this is where we do examples so that all of those ideas can get brought in and become final. All right, so here this is right in the beginning, the function is written in functional notation. That's why when it came to derivative, I went with using this notation for derivative. And the problem itself, before we even get into any of the question here, the problem itself uses 2 forms. So be aware that some other problem will come in that notation where it's just z equals a function of 2 variables. Okay, but now for this same function, we still have one more to go. So now how about f sub y, or that's for short, but then more formally, this is the partial derivative of f in terms of y. So now that tells me that, now I can erase all of this here. So now seeing this notation, it tells my mind to focus on the y variable being the main variable. Everything else aside from y, everything else not having y involved, we consider them either as constant term or coefficient. Okay, and so now, and I've already explained clearly what a term is and all that, and whether the main variable that we focus is in the term or not in the term. You should have now at this point you should have now know how to recognize that on your own. And so term by term, just like that, we're going to find this derivative in respect to y, term by term. So first term has no x. I mean no y. First term has no y because right now our mind is focusing on the y variable as the main variable. So that means having no y, the first term here is regarded in this context right here. The first term is regarded as a constant term. So taking the derivative, it gives me 0. Okay, and now we move on to the next term, minus 3x times y to the 6. Our mind is instructed to focus on y as a variable. So that means in this term right here, everything else in this product aside from the y variable is regarded as coefficient. So 3x is a coefficient. This 3x right here is a coefficient. All right, and so now what do we do between function and coefficient? When we take the derivative here in terms of y, then 6 multiplied, 6 being the power of y, we're going to multiply 6 down together with the 3x. It's going to be minus 18x times y to the 5th. Okay, so minus 18 because 6 multiplied with minus 3x right there. Okay, so minus 18x times y to the 5th. That's how I took the partial derivative of that term in terms of y. All right, and so now let's move on. Now I'm going to subtract. Okay, and now we're looking at, so this term has entirely just y, simply just y, so now it's easy. That's just like back to the thing we've been doing in the old days right there. So this is minus 15y squared. All right, so we're done for partial derivative of this function in terms of y. So now we can finalize that as f sub y equals minus 18x y to the 5th, okay, minus 15 y squared. All right, and that is our partial derivative of the function f in respect to y. That's how it's done for another one. All right. All right, so I can leave an FYT here for anyone to try. Okay, so how about f of xy can be all right, so that's my function as an FYT right here. All right, and so pause the video. We want to find, this is a function of 2 variables, of course. So we want to find, for anyone about to give a try independently on your own, I want you to find for me the partial derivative in respect to x and also the partial derivative in respect to y. Okay, so go ahead and pause the video and try it on your own right here. And once you resume, I'll just simply write down the final answer. All right. Okay, so at this point, assuming that anyone has already spent some time, so now I'm going to go ahead and provide the final answer right here. So partial derivative of f in respect to x is going to be 3x squared plus 8x y cubed, and that's the partial derivative of f in respect to x. Okay, and then for the next one that we're required to find right here, partial derivative of f in respect to y. Okay, this is going to give me 12x squared minus 20y cubed right there. And I mean 12x squared y squared. Okay. 12x squared y squared minus 20y cubed. All right, so now let's look into part B of our example. All right, so in part B of the example, let's look at how about z equals x squared plus y squared raised to the take the square root of x squared plus y squared. All right, so now this is where a notation like this is more suitable, like that. It's more appropriate because our function is written in equation notation. So it's a function z, and so here in this problem it's z, dz, dy, dz, dx, but be ready that maybe in some other problems when I wrote down it could be w equals something of u plus some, w equals something of u plus something of v, like that. So then it's going to be a dw, dv, dw, du, like that. Okay, be ready for anytime you're using this kind of symbol. Okay, so now to find dz, dx, and dz, dy for this problem, well, first thing, as usual, as you have already learned from calculus, from the differential calculus, then it's easier to write this as x squared plus y squared. That expression inside the square root, we're going to write it as the expression there, but raised to the power 1/2. This is just the preliminary step right there before we start taking the derivative. All right. But now I see inside expression and outside expression. So be ready for some chain rule involved. All right, but so now at this point, yes, let's find the dz, dx. I want to find the partial derivative of this function in respect to the x variable. So now upon seeing this notation right here, that notation instructed my mind and your mind to focus on the y variable. Focus on the, on the x variable as the main variable. Focus on the x variable. Okay, so having the x variable being the main variable, then the y variable here, anything else aside from the x that has no x involved, that's either constant term or coefficient. All right, but now sadly the function of x here is inside of this 1/2 function. So chain rule needs to be applied here. So everything you've learned prior to this point about taking derivative must be brought in. Okay, so now the chain rule says we have to take the derivative with the outer function, which is 1/2 times the whole inside of that, x squared plus y squared, but to the negative 1/2. That's the derivative of the outside function. And then I am going to multiply. Now the inside derivative function, there are two terms, but only the first term is in terms of x. The other term, there's no x involved. That other term right there is a constant. So now taking the derivative in terms of x of this inside function right here, I'm looking at 2x plus 0, because that y right there gives me a 0. All right, and so now that's all sudden made me realize that I've finished. I'm done with my partial derivative for z as a function in terms of x. Okay, and so here comes the final answer. It's going to be this 1/2 times x squared plus, I realize I ran a little bit out of space right there. And so 1/2 times x squared plus y squared to the negative 1/2 power, and multiply it. We can notice that the 2 here will cancel with that 2 times 2x right there. See, the 2 here cancel with that 2. All right, and so my final answer here will come out being x times x squared plus y squared, but in parentheses to the negative 1/2 power. That's one way how we can write our final answer right there. All right, and now I'm going to move on to the other board of mine. So now for the same function, let's look at dz, dy right there. All right, so dz, dy, and once again, before I get this, let me rewrite the function z here is x squared plus y squared inside of parentheses raised to the 1/2 power. So dz dy is, so now when we take that derivative, this symbol has instructed my mind to focus only on the y variable here as the main variable, the main independent variable. Everything else is constant coefficient. So now, but even the function in terms of y is inside of this 1/2 power function. So chain rule applies again. So now I'm going to look at 1/2 times all that x squared plus y squared to the negative 1/2 power, because this is the derivative of the outside function. And now I'm going to multiply with the derivative of the inside being, so the first term here has no y. That means it's a constant term right there. So it becomes 0 when we're taking the derivative in terms of y. And then I'm going to plus with 2y. Because this term here is clearly a term in terms of y. And so now that becomes 1/2 times x squared plus y squared to the negative 1/2, but multiply with 2y. And then I can cancel out that 2 right there. And now my final answer becomes y times x squared plus y squared to the negative 1/2. To the negative 1/2. All right. I ran out a little bit short in space on the other board, but I could have also mentioned this on the other in the earlier work as well. But this final function, this final form right here, okay, you can rewrite it also as y over. But it's usually not required. That's why, having it or not is not too important. You can also write that final answer here as y over square root of x squared plus y squared right there. All right. And so that's our final answer, but this is how I call that. This is the partial derivative of z in respect to y. Okay? And then for the other work that I've done earlier, the same part B right here, we can also write this as x over, and now square root of x squared plus y squared. All right, that is another way of writing that. But it takes some algebra to re-express the negative 1/2 square root right there. All right. All right, so now let's go ahead and look at some FYT right here. All right. And so in my, what I have for anyone to try independently, so how about z equals, so x squared minus 4y squared to the third power. Okay, so this is an FYT. I want you to give it a try independently. Okay, and then once you're done and resume the video, and just so in that way I'm saying go ahead and pause the video if you need to. And then once you're done right there, okay, then and resume the video, I will be just showing the final answer for this. Okay. All right. So now, assuming you have spent some time and work on your own problem right there, then now dz dx is going to be, so now 3 times x squared minus 4y squared, okay, but multiply, and this is dz dx right there, so it's going to be 2x, okay, or all together we can write, so this is technically the final answer right here, but we can also rewrite all together as a 6x times x squared minus 4y squared. That's a different way of writing that. A little bit simpler. Okay. And then the dz dy, we can find that derivative as 3x squared minus 4y squared, okay, times, and now it's going to be a minus 8, minus hy right there. So that's one way you can write your final answer without simplification, okay? Or you can write your answer as minus 24y and then x squared minus 4y y square square. That's the answer for the dz dy. All right. All right, and so now let's look at another one in our problem right here. Okay, so here, what about part C of our example? So let's look at how about z equals 5 to the 4 times e to the 2xy. All right, z equals 4 times e to the 2xy. All right, and so now the function here itself is exponential. Okay, but now to find dz dx, my mind is telling me, once seeing this symbol, that my mind is telling me that I need to focus on x here as the main independent variable. Okay, that is a coefficient. And then in this portion right here, 2xy right there, then x is the main variable. So 2 times y is the constant is a coefficient. Okay, so that now means taking the derivative in terms of x, 4 is a coefficient, we leave it there. And now it's going to give me e, the derivative of the outer function is e to the something, Okay, so now e to the 2xy, that's the derivative of the outer. But now I need to multiply with the derivative of the inside function, which is done by according to the chain rule. Okay, according to the chain rule. So in that way, now x is the main variable, so 2y is going to be what remains after taking the derivative. All right, and so now we can rewrite all of this here as an 8y times e to the 2xy. And that's how we're done for that one. All right. And then now let's look at the dz dx right here. All right, and so again, now and I need to correct this. This is dz dy here. And so again, similar to how I did the earlier one, here my mind is telling me that I need to focus on the y here as the main variable. The y as the main variable. And then anything else is, see, the 2x here is a coefficient. And then there's another coefficient in front of the function e right here. All right, so now it's going to be 4 times e to the outer derivative is going to give me just e to the 2xy. That's the derivative of the outside function. And then I'm going to multiply with the derivative of the inside, which gives me just simply 2x. Because now with the inside of that e to the something function is the inside of that is a 2xy. But y is the main variable, so taking the derivative of 2xy, we get just 2x. All right, the derivative in terms of y. All right, so now the final answer comes out being 8x, okay, e to the 2xy. All right, so that's what it is. That's how I have found the the partial derivative of z in respect to y. All right. And now let's look at an FYT problem for anyone to have a chance to try independently. So as an FYT, all right, so as an FYT, let's look at how about z equals 5 e to the 4x plus y. Okay, 4x plus y. Okay, so now in this work right here, go ahead and pause the video, okay? Spend your time working on that, and when you resume right there, I will just simply, write down the final answer. Okay. All right, so now dz dx here is going to be 5 times e to the 4x plus y, okay, times 4, which together is 20 e to the 4x plus y. Okay. Or we can also stop at this answer right here. And that's my answer in two different forms of writing it. You can also, and now dz dy for this function is going to be 5 e to the 4x plus y, but times 1, all right, which is simply just 5 e to the 4x plus y there. I mean, these are just exactly the same form where in the last final one, I skipped the 1 right there. So really, there's just only one way of writing this answer. All right. Okay, so let's look at another one, and this should be the last one in our example over here. And so there will be no instructor that can cover enough examples out there about taking the partial derivative. So I call this one here the last one right here. And if anyone viewing this lesson is a student who learns directly with me, you will have a way to contact me for additional clarifications. Okay, so the D here. So how about let's now switch back to the traditional functional notation right here. So how about I'm going to call this natural log of an x squared plus y squared. Okay. F of x comma y equals natural log of an x squared plus y squared. And so now our function is written in functional notation. So I have to stick with these two symbols instead of the dz dx or dz dy thingy. So now it's going to be f sub x, which is partial derivative of f in respect to x. This gives me, see, so the function in respect to x is also inside of the logarithm function. So chain rule applies again. So the main rule about logarithm is that when you take, anytime we take derivative of logarithm, we have to take the reciprocal of the inside. So now according to the chain rule, we have to take the derivative of the outside first. So the outside is logarithm. So that's why I said about take the reciprocal of that x squared plus y squared right there. Now it's 1 over x squared plus y squared. And now we're going to take the derivative inside of log right there, of the function inside of log, and primarily focus on x as the variable. So now it's going to multiply with, so the derivative, that is a constant term, so it goes to 0, plus, and now that is giving me 2x as a derivative in terms of x. Because taking derivative in terms of x on that term is just a constant, it gives me 0. And so now my final answer, we can put it together in one fraction. So it's 2x divided by x squared plus y squared. And we're done for that one right there. And so now this partial derivative right here in the end, I mean, I should have also mentioned this in the earlier problems here that we've done, but the partial derivative also turns out to be some other functions in terms of two variables, x and y. So sometimes we can also see people writing the following symbol, f of x comma xy right there. Okay, that's another way of writing that. So now let's look at the partial derivative. The partial derivative of the function f in respect to y right here. All right, so the work is extremely similar. We're first going to have to apply the chain rule, and we take the derivative of logarithm. So it's 1 over x squared plus y squared, just like that. All right, and now we multiply. Now we take the derivative of the inside. But the inside this time, we're going to focus on the derivative in terms of y. So the x term here, completely no y. That x term will go to 0. So here I'm looking at 0 plus 2y, because we're looking at taking the derivative in terms of y. All right, and so now the final answer here comes out to be, it comes out. Okay, so 2y over x squared plus y squared. That's my final partial derivative in terms of y variable. All right. And now as an FYT, before we leave this example for anyone viewing the lesson for here, let's how about look at, all right, so how about f of x comma y equals to natural log of x squared minus 4y squared. Okay, x squared minus 4y squared. All right, so now go ahead and pause the video, spend your time working on that, and then once you resume the video, I will just simply write down the final answer. All right. All right, so now hopefully you have spent enough time on working on the problem here. The final answer comes out as following. The partial derivative of f in respect to x here as a function of two variables, okay, is going to be, so now my final answer is 2x over x squared minus 4y squared. That's the answer for that. Okay, and then on the other hand, what I found, partial derivative of f in respect to y as a function of x and y is going to be minus 8y over x squared minus 4y squared. All right, and that's how we find the answer to, that's how those are the answers of this of the two partial derivatives. Okay. All right, so in the end, after looking through the whole example 1 right there, including all of those the FYT that I also included in example 1, so there were a lot of practice problems for us to look at. Right there, some practice problems you work on your own, and some other ones I led the way right there throughout the steps. So in the end, you can see that taking the partial derivative, but finally at the final answer, the partial derivative generally was another function of x and y. Okay. So partial derivative, so for example, the one we just now finished in example 1, okay, the one we just now finished, for example, f of x was, f of x and y, okay, was originally as a function, natural log of x squared plus y squared, and then so I only need to arrive at 1 right here. The partial derivative in respect to x, okay, I found that to be 2x over x squared plus y squared. And then so now I can clearly see that this is another function in terms of x and y. It's not the same as the beginning function, clearly not. Okay, but it's also another function in terms of x and y. So now in that way we start thinking, so can we substitute values, because now treating a partial derivative as a function as well, multivariable. Okay, then can we substitute values for both x and y, for example, right, to get an output of the derivative? All right, and the truth is yes, we can. So let me demonstrate that through the short example in coming right here. All right. So now I can just call that example 2. All right, but then in this example, how about let's start out with the given, and the f of x y right here equals minus 3x to the 5th plus 6xy cubed plus 4y to the 4th. So that's a function of two variables given to us right here. Okay, and so now we want to evaluate, or sometimes your assignment some textbook here and there may refer to this as find the value. Okay, so or here I more commonly call that evaluate. So what do we evaluate here? Let's say evaluate fx, okay, the partial derivative of x in respect to x here at the value, how about 3, 4. So now seeing this symbol, it means the following. Our first responsibility is to find the general fx as a function of two variables. So the work now is just like how we have done that in example 1. All right, so here we go. Partial derivative of f in respect to x as a function of two variables generally comes out straight out from this. So now first term here gives me a minus 15x squared. Just that, no doubt about that. middle term gives me, okay, plus, so now 6y cubed, okay, and assuming that you've got decent enough in terms of catching up with this understanding, so when it comes to taking this partial derivative, I don't have to explain in too much details anymore. Okay, so the middle term here, taking the derivative in terms of x, right? I come out with 6y cubed. Okay, and then I'm going to add with now 0 because simply this is no x, right? So this is just a constant term, and then being a 0, I'll just leave that out. All right, so now clearly it's a function of two variables. And so now to find that value, all I have to do now is, so the partial derivative of the function in respect to x, but substitute it in 3, 4. So now with our understanding of function of two variables, in the way how this was written, x is the first number here is x, the second number is y. It's just indicated here. So now 3 here must be substituted for x, and 4 must be substituted for y. That's all I need to clarify like that. And that's the reason why we need to spend a little bit of time looking and to understand what the multivariable function is all about before we get into doing partial derivatives. Okay, and so now here I'm looking at minus 15 times 3 squared plus, and now 6 times 4 cubed. All right, and so at this point I need to swing by my calculator at the computer station right there to graph a final answer. All right, so my final answer comes out to be minus 831. All right, so that's the answer for this problem in part A right there. Okay, and so now similarly, let's look at part B right there. All right, so now for part B of the example, let's evaluate partial derivative of the function in respect to y, okay, but at the value 3, 4. All right. And so once again, the idea is exactly like what we did in part A right there. But now instead of taking fx, here we're taking fy. Partial derivative of f in respect to y. All right, so we're first going to find the partial derivative of f in respect to y as a general function of two variables, x and y. And anyone learning this is welcome to do this independently on your own right there. So now it gives me 18x y squared, okay, plus, and now the next term is taking the derivative in terms of y. Here we're looking at 16y cubed right there. Okay, and so now once we've had to this partial derivative in respect to y right here, clearly speaking, it's a function of two variables, or needless to say. Okay, and so now evaluating this partial derivative in terms of y at 3, 4, it means we're going to substitute 3 for x and 4 for y in every term of your problem right there, of the current partial derivative. So now it gives me fy, so that means fy at 3, 4, okay, must equal, so now I'm looking at 18 times 3 times 4 squared, okay, plus, and now it's 16 times 4 cubed. All right, and so now I'm going to need to swing by the calculator at my computer station to graph that final answer right there. All right, so now I'm looking at 1888. That's my final answer after the calculation. All right. All right, so after investigating about two examples, we've been focusing on functions of two variables. Okay, but see, once we can find partial derivatives on functions of two variables, then why not extend that understanding to finding partial derivatives on functions of three variables, and even more. And as a matter of fact, in my demonstration problems, when I was introducing about the concept of partial derivatives, I already brought up that that function, the f equals a p times e to the kt right there. Okay, and so we have seen that taking partial derivatives on function of three variables exist. And even, I may not include those kind of problems here, but taking partial derivatives of functions of four variables or five variables are entirely possible out there. Okay, so here the most for in this lecture I'll just stay with as high as or the most three functions of three variables. Okay, so let's look at some example of how we can find the partial derivatives on function of three variables. All right, so now let's look at example 3. Okay, and so I want to find, fx or some du dx, okay, and then fy, okay, or some du dy, okay, and finding f z right here, because now the function has three variables, so there has to be expectedly three partial derivatives existing out there, or we can call this as some du dz. So now we're finding that. All right, so let's look at part A, and I don't think I need to make this example too lengthy right there. Okay, because you already got a good hang out of out after a lot of practice over example 1 and example 2 on those functions of two variables. So here we can just focus on about a couple of those. So what about so here, how about let's look at f of x, y, and z. Okay, and so now I'm about to write functional notation. So that means when we're getting into using the partial derivative, then we use these kind of symbol over here, this kind of symbol. Okay, so now how about the function f of x, y, z is defined to be for x squared y z cubed plus 2xy z squared. Okay, so something like that. All right, and so with this function right here, yes, so as I said earlier, the function is of three variables, and the function is written in functional notation. So when it comes to taking when it comes to taking the partial derivative, we have to stay with this convention right there. Okay, so now for partial derivative in respect to x, okay, and of course it will be function of three variables. So now I'm going to look at, so first term here, we're going to focus on x as the main variable, and everything else, see, and this, the reason I still want to mention about function of multiple, even more than two variables, because aside from the main one that we focus to, anything else, maybe a lot, see, there's y, there's times z cubed, and then times the 4 over here, but everything else in one term right here, everything else aside from that x squared right there is considered as one package of coefficient. So that means the real thing that matters for us to take the derivative is to bring the power 2 on the x down, okay, and then that power is reduced by 1, but everything else is coefficients. So now I'm looking at 4, but times 2x, okay, times y times z cubed. That's how it's done, okay, for the first term right there. And see the power on the x reduced by 1. And then I'm moving on to the next one right here. See, I'm focusing on the x. So the x here is going to have power 1, so 1 multiplied down. So it's 2 as coefficient times 1 times x. And we don't need the x anymore, okay, and then times y times z squared. So my final answer here comes out being 8xy z cubed plus 2y z squared, and that's how we're done with the partial derivative in terms of x. All right, and so now after this one here, let's look at the next one. So we have to find fy right here. All right, so for fy that we're heading out for, it's a function eventually of three variables. So first term in my mind, my mind is telling me that in the first term here, I only need to focus on the y variable. That is a coefficient. So 4x squared is a coefficient. The z cubed is also another coefficient together. And so this term here currently has y to the first power. So when we take the derivative, so same way the power 1 multiply it down, so I have simply just 4x squared. The y is to the power 0, so we don't need to write that anymore, but then still multiply with z cubed. So first term becomes, after taking the derivative in terms of y, 4x squared z cubed. And then we move on to the next term. Okay, the y variable is here. So now it becomes 2x z squared, similar to what we did in this term right there. And that's how we are done for the partial derivative in respect to y of this function. All right, and now let's look at when it comes to partial derivative in respect to z right here. Then, well, and of course it's a function of 3 variables. So now my mind is telling me to focus on each term here. Focus on the z variable in each term. Focus on the z variable in each term. So the first term, everything else here is a coefficient. Everything here is a coefficient. Okay, aside from the z variable. So now the z variable here is z cubed. So now all of that here is coefficient. So now taking that derivative in terms of z, here's how I'm doing it. All right, so 4x squared y times 3 z squared. Because that's how we're taking the derivative in terms of z, treating everything else as coefficient. That's how it looks. And then I'm going to add, and now I'm going to rewrite the coefficient to xy. I'm going to rewrite the coefficient, and then taking the derivative here to z. All right, and so now I can simplify my expression here as, this is now 12 x squared y z squared, and then plus 4xy z right there. That's my final answer for that. It's a partial derivative of f as a function in partial derivative of f in terms of z like that. All right, so that's how we found 3 separate partial derivatives in terms of z right there. Okay, so now let's look at another problem right here. All right, so now with this problem, I'm looking at, how about in part B right here, let's look at u as a function equals e to the xy z squared. What's that? E to the xy z squared. All right, so du dx. Let's find that first. It's a function of 3 variables. So my mind is telling me to focus on x as the main variable, but x now is being part of the inside function of this e to the something. We have e to the something, and then inside of that there's a x times y times z squared again. And so now we need to bring in chain rule. Okay, so the chain rule says we take the derivative of the outer function, which is the e to the something. Because see, I wrote it down earlier and writing e as an outer function, and then I wrote in that inside part after. Okay, and so now it's e to the xy z squared remains the same here, but now I'm going to multiply with the derivative of the inside. That's the inside right there. Okay, and so now I don't think I need that anymore. So the derivative of the inside underlined right there, so it's going to become, now we focus on the x variable, so now it becomes just y z squared right there. All right. And that's how I'm done with my function. And we can just simply rewrite this as y z squared times e to the xy z squared. That's how we're done with that. All right. And then du dy, partial derivative of u in terms of y. Here I can do as following. So it's very similar to how I've done that in the earlier partial derivative. I need to retain that e to the xy z squared. I need to retain that, but then I multiply according to chain rule the derivative of the inside, but this time in terms of y variable. In terms of y variable. So now that gives me x z squared. All right, And now I can rewrite that as x z squared times e to the x y z squared. That's my partial derivative in terms of y, of the function u, but in terms of y. Okay. All right, and so the last one here in this part B of the example 3 over here. So how about d, du, dz? All right. So again, just like what we have done right here, we have to use a chain rule. The derivative of the outer function gives me the remaining, just that, the e to the x, y, z squared that remains here. But now I need to take the derivative of the inside here, this inside part right there, but focusing to z as the variable. All right, so now I can put it out. So here I'm looking at x times y, but times 2z, because x, y is the coefficient, and then now we take the derivative in terms of z for that z squared right there, that's, which gives 2z. And so now that's all together, I can write this as 2 x, y, z. Okay, and then we multiply with e to the x, y, z squared. And that's how I'm done with the du, dz of this function here. Okay, the partial derivative of u in respect to z as a variable. All right.